Good. The volume's on too high, I guess, a little bit too high. Just cut it back a little bit. So, I'm gonna grab a water, I guess, and I think we started. Be right back.
Yeah, absolutely. Yeah. A lot of training stuff. Yeah. Yeah, I was gonna put it on a memory stick. There we
I think
go.
it works.
You might delete it first.
Yes, you can.
Yeah, that works.
Yes, that works.
All right.
No, I'll just leave it on the browser, I suppose, right? But it's also available on stuff.
Is there a regular whatever apps or
Like on the Acrobat.
yeah.
Yeah, maybe
Yeah,
that
they
works.
have weird. That be full screen. Oh. Yeah. Okay, forget it. Forget
You
it.
can just-
Abort. Abort.
There should be a full screen here.
That's okay.
Hmm.
We're gonna stick with where'd it go? Oh man.
Maybe it was in Edge.
There.
Yeah. Let's see.
There you go. Oh, now we got two copies. There we go. Okay. All right. Yeah.
Okay.
You can switch back
All
to
right.
the other one.
Yeah. Okay. Mhm. So, okay, so I think we should probably get started. A little bit of time, yeah, let me get the mic here. We should get started. We had a little problem with the setting up the computer and all. Yeah, the Wi-Fi and everything. So, but anyway, so thanks for coming, everybody. And anyway, this is we're trying to every year we have a soft matter symposium sponsored by Procter and Gamble, and basically it's been going on for 3 or 4 years, and we've had a series of speakers. And the idea is to bring in soft matter speakers that are leaders in the field, and then we have interaction with them with UC and P&G jointly. So we have kind of a collaborative effort at trying to activate soft matter in Cincinnati. So this year we have Sanat Kumar from Columbia, who's has a long history, I guess, in polymer science. So he did the BS degree at Madras, IIT, and then went to MIT, worked with Reed and Suter, and did supercritical solvation of polymers. And then he went to IBM Albany, and after that, and interacted for Doyoon, and then worked also with Tom Russell there. And then afterwards, we went to Penn State and had things to do with Colby and some people. So he's kind of touched all the major polymer people. And then from Penn State, he went to Rensselaer, did some work with Linda Schattler, and began, I think at that time, nanocomposite work, and became the leader in the field of that, polymer nanocomposites. And then went to Columbia afterwards, became head of chemical engineering there, and now he's doing research in polymer recycling, and also this AI machine learning attributes. So it's really a pleasure to have them here. The talk is called machine learning for developing understanding of soft matter systems. So we can welcome Sanat. And also, so there's 2 other speakers. There's a UC, there's a P&G speaker, Matt Barker, and George Stan from chemistry. So they're both in the machine learning AI things. And in between, we'll have an award for the practical to Sanat, and then Gerard Bailey's going to give a little bit of a kind of motivational speech, I think, about interactions, more or less.
Maybe
But
you should do that
yeah,
first. Gerard.
yeah. So anyway,
Thanks, Greg.
yeah, sure.
So many, many thanks. Can you guys hear me properly? Do I need this thing even? All right. That sound that goes off in the back, that's supposed to keep you guys awake. So it'll go on every couple of minutes, right? This is a small enough audience. And, you know, the slides are not being shared. So it's your job to go share the slides, right? I delegate really well, right? So what that is supposed to be a sort of a pointer to say, ask any question you want. I have really nothing, no agenda. We'll go as far as you want. I have my usual quota of 200 slides. So even though I can speak really, really fast, I don't think I want to do that. All right. You guys got your act together? I think so. All right. What do you think, Peter? All right. So, I tell my students that we don't really learn about, we're not machine learning people in that we don't develop tools in machine learning. I see myself more as a practitioner, right? So I'm taking the tools that exist and apply it to the physical sciences. So that's sort of what I'm going to be telling you about. This is primarily the work of 2 students in my group, Will Marshall and Tejas Shastri. They're both graduating. They're going to get out of here fairly soon. And it's a collaboration with this guy, Matt Carbone, who is at Brookhaven National Labs. And Matt's really my bridge into all the physical sciences, okay, into the computer sciences. Sorry, I'm a little distracted. I'm waiting for this stuff to get all organized and then. They're all taken away? Cool. And Peter, if there's questions online, please, if there's anything, just tell them on the chat to shoot questions out, right? All right, I know most of you guys are going to go to sleep in the next 20 minutes or so, right? So I just want you to take away this big message, right? That I'm going to talk about machine learning in the physical sciences, right? And what the point that will keep coming back over and over and over is the lack of data, okay? For all kinds of systems that we deal with, getting between 100 and 1,000 data points is a really big deal because that means somebody had to go into the lab and do an experiment 1,000 times over, right? Now, contrast that with what happens in the social sciences. For example, people who do Google, So when you go watch a movie on Amazon or whatever, it tells you, based on your interest, I'm going to ask you to watch this next movie. They're basing it off human populations, which is 10 to the 9, a billion people, right? So the numbers of data they have is much, much, much larger. So all the tools that have been developed are for these very large data sets. And when you guys awake? Okay. If you're between 100 and 1,000 data points, you're like really screwing around at the edges where noise kind of dominates your data, right? So that'll become very important as I go through it and talk. And the other thing which I'll come back and talk about a lot today is the quality of the data. It's the quantity and the quality. And these are things we normally don't think about, but when you start coming to machine learning, it becomes the sort of dominating problem. So I'm going to give you 2 short vignettes. One is a very classic way that people in the soft materials community use machine learning. And what I'm trying to do is not just fit data with machine learning, but actually try to derive some understanding, okay? So the first one is basically the way people do it now. And then the second part is where I think is really new stuff, which is where I think we're starting to break new ground. And that's the part that's unpublished, it's novel. And so the first part is almost sort of telling you what tools we have. The second one is telling you what we can start to do that's new. And again, please ask questions as we go. Okay. Maybe we can shut that off, you think? We don't know how to, okay. We'll just keep that going, just as background music or whatever. So my group, do you know how to shut that off? Okay, cool. And my screen, all right, my screen will actually disappear in this process, but that's okay. All right, so my group, we do lots of things, right? But one of the big applications we think about is for gas separation, all right? And why do I care about gas separation? If you're in a plant that is generating electricity, you're producing CO2, and CO2 comes out mixed with nitrogen and oxygen. You want to separate CO2 out, right? And the kind of separation you're dealing with is very subtle, right? So here, CO2, its size is 3.3 angstroms, oxygen is 3.5 angstrom, nitrogen is 3.6 angstrom. So you're looking at sub-angstrom size separation. Very hard separation to do. All right? The other kind of separation you're doing is natural gas from CO2. Again, you can see it's a half an angstrom size separation. So these are extraordinarily hard separations, but there's a whole industry that's evolved around it, okay? And what they do is they tend to use polymeric membranes. That's what I've sketched here. Typically, they'll take a glassy polymer membrane and they'll make a film. And some schmuck gets to go out into the lab. Why is it just suddenly go up in volume? Do I really need this thing? I mean, can I speak without that?
People online.
Oh, that's true. I didn't think about that. Yeah, okay, cool. I hate this thing, by the way, in case you haven't gathered. Sorry, so the idea is you make a polymeric membrane, and then you contact it with this upstream gas. What am I doing here? This thing stopped working, so, oh, it is working. Okay, so you have this up. So on the left-hand side, where you have the gas mixture, right? That could be a mixture of CO2 and oxygen, for example, CO2 and nitrogen. And on the other side, you want to get pure CO2 and you want to get it at high flux, because those are the 2 figures of merit. So when you start designing these membranes, does that work? All right, thanks. Just remember to take it back. So you want to get high flux, high selectivity. And so the figures of merit start turning into how much stuff goes through, which is the flux, okay? And that by fixed second law is the diffusion constant, the concentration gradient of the gas in the membrane. And after doing a little bit of math, you figure out that you've got the pressure drop across the membrane, the thickness of the membrane, those are things you control. But up front is a product of this constant called the diffusion times the solubility, and that's called the permeability. And so to get high flux, you want a polymer with high permeability, which is a product of that. If you want to get purity, high purity, or high selectivity, you take the ratios of the permeabilities, and you want to make that as large as possible. So those are the 2 quantities that you're designing for, all right? Now, people have gone, and over the last 50, 60 years, people have investigated something of the order of 500 canonically polymeric membranes, just going in the lab, brute force testing it, okay? And when you do that, you get plots that look like this. So here's a plot here, the permeability of CO2, the selectivity of CO2 to methane. So this is for 2 particular gases. These data points here, each one corresponds to a separate polymer, okay? And you can see here, there's about 500 data points. A few things immediately strike you. You see that there is a negative correlation, which means as the permeability goes up, the selectivity goes down. And that makes sense because you're sieving based on size. If I make the sieve size coarser, more stuff goes through, but it's less selective, right? Now that sounds great, but I couldn't tell you which polymer corresponds to high permeability. I don't know which one corresponds to low permeability. There is no correlation between the polymer structure and separation behavior, okay? So what happens is basically you go in the lab, you test, and then, in the late 2000s, people started figuring out if you make the polymer backbone very stiff, those are the blue points, you start to do better. You're moving up towards high permeability, high selectivity. So there's really no understanding except for this one very simple paradigm that stiffer polymers do better than flexible polymers. But beyond that, there are no design rules, okay? So there are two questions here that I'm after. The first one is, can I start to figure out the mechanism for separation? I told you it had to do with the sieving mechanism, but how do I go from polymer structure to sieve size? Or how do I understand the mechanism for separation? That's unknown. That's where I'd like to be understanding. But to start with, I just say, can I do better? What do I mean by that? They've tested about 500 polymers. If you go look in the literature, there's a database that has 10,000 known homopolymer structures that have been synthesized. So rather than send some schmuck into the lab to test out 10,000 more polymers, 500 polymers took 50 years, so you can do the math. It's going to take a while. Can I use machine learning to say which of these remaining untested polymers might do better? Okay, so that's sort of the low-hanging fruit. Longer term, I'd like to understand the mechanism for separation. Okay, everybody following along up to now, right? No questions. All right, cool, fantastic. I'm clarity itself on Friday afternoon. So here's sort of the roadmap of what we want to do. I know somebody can go in the lab and make a polymer. The polymer has some structure, right? So polymers have two things. One is the structure at the level of a monomer, and then it's how long the chain is and whether it's amorphous or crystalline or whatever. So you have to describe that. That's the polymer fingerprinting part. And basically what machine learning is going to do is you tell me something about the polymer, and if I tell you the permeability for a gas through that particular polymer, then I can train the model on that so that it'll start giving me predictions. Okay, and so that's sort of very roughly the roadmap of what I want to do. In here, the few things are, how do I take a polymer structure? You guys have questions? You two guys back there, you have a question? Ask. I can do better than you explaining to him, probably. Yeah. So I'm just saying you have a polymer, right?
Yeah.
A polymer is made up of a monomer connected together. So I have to describe either the monomer, I will describe how it's put together, how long the chain is, and the local tacticity or whatever. The local arrangement of the monomer is all regular or irregular or whatever. Yeah. It could be. It could be. It could be. But what I'm going to tell you in a moment is that it doesn't seem to matter. As long as I'm dealing with homopolymer chains, it doesn't matter how long the chains are. It doesn't matter what the tacticity is. The only thing that matters is the monomer structure. So this different cartoons I have is the structure within a monomer. That's where I was going. You stole my punchline. Thank you. That's okay. Everybody understanding this, right? So the first surprise we found is the length of the polymer doesn't matter. It's whether it's amorphous or crystalline doesn't matter. Only thing that matters, yeah.
Does not matter.
Yeah, the only thing we are finding is the monomer structure is the only thing that matters. So what I haven't told you here is that this level of fingerprinting I'm going to do is within the structure of the monomer, within a monomer. And within that, I can start to say the connectivity, right? How far I want to go. So n=1 tells me whether I have a carbon, where the carbon is connected to something, and then so on. I can build up a hierarchy of structures within that monomer itself, and each of them gets starting represented into this vector, which is called a fingerprint vector. All right? So basically, I'm going to take every chain, describe it by its monomer. I'm going to fingerprint that. That's going to be correlated to a permeability, and I'm going to assume or try to find that correlation mathematically. That's all machine learning is. It's dumb as nails.
You could take a carbon to polyethylene.
Yep. Yep.
2 carbon to 10 carbon.
No, that's exactly right. So you can do that, right? So for example, you pick the minimum repeat. Okay? And then you say, this is my minimum repeat. What can I get out of that?
Coil. And that coil repeat would be repeat. Right?
No, but so what I'm telling you, what seems to matter in our case is the minimum repeating unit is what I'm going to call the monomer. Nothing. I don't care about superstructure at all. It's just surprising. Okay? And there's reasons for that, I believe, but starting out, this is an empirical observation. So that's basically all we do. We're looking within a monomer, and you get all these kinds of, things in the way the monomer, the carbons and the hydrogens and chlorines and oxygens are connected, and that's the fingerprint vector that I'm going to. So what does machine learning do? It's sort of really dumb. So X is that fingerprint vector, right? Y is my permeability. And basically machine learning says there is a linear transform, W transpose, that goes from the space of fingerprints into permeability. And so the trick is to determine this linear transform, W transpose. And if I can do that, that tells me how I can go from a certain monomer structure to a certain permeability. It's really stupid as hell. So there's a couple of assumptions here. I'm assuming the transformation is linear. You can do better than that, but I'm going to start there. And it's always Occam's razor. I don't need to do anything more complicated than I need to. Linear transform works, I'll run with that. If not, I have to do something more complicated. So basically what I'm saying is I have to minimize the error in the prediction. So there will be the experimental permeability, the predicted permeability, the difference of that squared. I minimize that quantity summed over all the polymers that I'm testing. And then this is the other piece that you add in. That's called regularization. That tells you this matrix W, I'm going to insist that all the values of the matrix elements be as small as possible. So I don't want a matrix that has large positives and negatives, right? Because that sort of makes the problem more complicated. It tells me I can take large positives, large negatives, add them up to give a small number. And that's always a dumb thing to do, right? So by putting in this regularization thing, I make the elements of W as small as possible, okay? So that's basically the function that I'm going to minimize. And to minimize that, I'm going to determine the elements of W that give me the minimum. That's all machine learning is in this particular construction. There's more sophisticated ways of doing that, but for the moment, this is sufficient. This is an optimization problem. I know you guys don't want to see math, so I'm not going to show you the math, but this is basically just minimization, which I can do. Now, there is something important here. So I have 500 data points, right? What you always do is something called training and test set. So you take the 500 data points, randomly break it up into 80%, 20%. You train, meaning that you determine W on this 80%, and then see how well it does in the remaining 20%. And that's always make sure that you're doing a good job representing the data you've got. And then once I've trained the model, then I can go see on the other 10,000 polymers on which I have not tested, whether I can find better elements. Now, what that requires is that the 10,000 polymers must have the same motifs that I've seen before, but that's the only requirement I need at this point. Everybody's still doing okay. All right, cool. So this is how well it does. So take one, take your favorite. Let's take CH4, okay? This is the actual experimental permeability. That's the predicted permeability. For reasons that are relatively obvious, we plot the log 10 base because the permeability varies over orders of magnitude. By fitting to the log, you give all permeabilities equal weightage. The blue points are the 80% on which I determine the W transpose. It does a very good job. That's 45-degree line, tells me I'm completely accurate. And then the remaining 20% is what I'm testing on. And you can see it's not doing as well as in the blue points, but still doing pretty damn well. Okay, and you can see across all these different gases, it's doing a pretty nice job. Okay, so I have a W transpose that is determined. That seems to work pretty nicely. You're squinting. Are you doing okay back there? Any question? No? Okay. Anybody have questions at this point? Yeah, sure.
Selectivity is another part.
You can do anything you want, right? Because that Y, the element Y, in this particular case, I just put in for one variable, but you can set it up for multiple variables. I'm still optimizing. It's a single W transpose. It's just choosing the optimization function, right? And then it's a question of how do I scale them? Do I use log or not? How do I make sure they both are represented the same way? So the way you fix that is make sure every variable goes 0 to 1 and occupies 0 to 1 uniformly. As long as you do that, you weigh each variable the same manner. You can also, for example, saying permeability is more important than selectivity. You can put weights out front. You can play all these games. I mean, it's your imagination, basically. But it's a straight optimization problem, right? All right. So now with that information, I can start to see if I can find a polymer that is better, which is sort of the goal, right? So let's take this one, oxygen, nitrogen. So this is a plot of permeability versus selectivity. That line you saw there on top, I didn't talk about that line earlier, and I want to go back and do that for a moment. So these lines here are called the upper bound correlation. So it tells you in 1991 when it was drawn, all the points that were experimentally known were below that line. As a function of time, that upper bound is moved up. Today, that dashed line is the best upper bound. So it tells you all the polymers fall below that line. So that's the current state of the art, okay? So if you want to find a polymer that's better, you have to be above that because you have higher permeability, higher selectivity. So that's what I've done here. If you look at oxygen, nitrogen selectivity, this line here is currently the very best. Those are the 10,000 polymers that are known in the literature, out of which 500 have been tested, 9,500 have not been tested. And these are the predictions for all of those. And you see most of the points fall below that line. The green points fall slightly above the line. But this tells me for oxygen, nitrogen, the current polymers that have been tested already are doing as good as they're going to do. Okay? So there's no point testing the other 10,000. Whatever you gain is going to be slightly above the upper bound correlation. On the other hand, you go to CO2, methane, you can see lots of data points about the upper bound correlation, right? So it tells me I'm expecting of order 100 of these polymers that have not been tested to actually do much better than the best ones that have been tested. So here is a place I can go and see how good machine learning really is as a means of finding new polymers. So what we did was we picked out two of those points. That's that red cross and the blue cross. That's the prediction of the machine learning along with the error bars. The corresponding structure of those monomers are here. I went to my synthetic collaborator, Brian Bensowitz, said, can you make those polymers? He said, yep, of course I can, because it's already from a database. He made the polymers, we tested them, and the experiments that came back on those correspond to the blue circle and the red circle, and they both are within one error bar of the predicted machine learning. So it works. Method works beautifully. All right. So here's a way of discovering materials from those that have already been made, which are better than the best ones that have been used up to this point. So as a way of finding better polymers, it works very nicely. Everybody happy with this? Haven't lost you yet. Okay. Yeah. So what you do is you make this polymer. It's in solution. You cast it, typically in a well, right, in a beaker. Let it dry. Then you have a film. You press it into, the way the permeation setup works, you have a brass plate with a 1-inch hole cut in it. You take that film, you slap it on top, you glue it down. So now you've got this plate with the hole in it with the polymer on top. Downstream is evacuated. Upstream, you put the gas you want. And watch, and as a function of time, as the gas goes through here in the bottom chamber, the pressure will go up, right? Initially, it'll be nonlinear. Eventually, it'll go linear. And that linear increase of pressure is directly proportional to how much stuff is going through. So once you get the slope of the pressure increase, use very simple ideas. You know the cross-sectional area, the thickness, you can work out the permeability. I'm sorry, say that again? Very good question, right? We didn't even ask that question. And the reason I didn't ask that question is because those 500 data points in the literature, no one tells you how they made the film, right? So I'm on par with what they did. Later on, I'll show you that's really, really important. But knowing the protocol is really important, but for this one, it doesn't seem to matter. Very good question. Everybody happy? Yeah.
You think it's the way you did the fingerprinting that allowed you to extrapolate to the untested polymers? Were many of them similar enough to the 500 that were tested?
Evidently, right?
Yeah.
Evidently, yeah. We'll come back to that in a moment. It's really important. Again, very important question, right? Anything else? Okay. So this tells me at this level, it works very nicely. So what I did was I took this fingerprinting, right, that told you how far along the monomer I go, and the further along I go in the monomer, the more detail I have, right? That's really important, but all I need to do is describe the monomer structure. So we said, let's get really ambitious. Up to now, I've only used the 10,000 polymers that have already been made. Can I use the machine learning as a way of coming back to design polymers that might be even better? Can I do even better by coming back and designing the sequence of monomers itself, right? So that's a technique of optimization where you assume a set of structures, predict what you get, and then you use something like the genetic algorithm to keep playing with the monomer structure and finding your way to an optimum, okay? We started doing that and we got complete garbage. Got nothing at all that came out, okay? And I told my student he was a loser and all this usual stuff that advisors do to their students. This went on for a while. And then he went online and came back and told me that apparently there's a big problem what we're doing. So what we did is the following. We take all these monomer sequences, right? And I told you about how we fingerprint. And I said n equals 1, 2, 3, 4. That tells me I start with a carbon, start talking as I go further away, how much correlation I have. So I generate a lot of information about the neighborhood of each element of that. This is a whole crap load of data. Fingerprinting data gets really out of control. So to reduce the fingerprinting, they use a technique called hashing. Okay, and hashing is a way of reducing space. Now, where is hashing used? Once you start asking that question, you understand. Hashing is used when you enter a password on your ATM machine. So you enter something, or on your computer when you enter a password, before it sends it out, hashing takes the password you entered and sort of uses an algorithm that maps it one way into something else that the computer will recognize, okay? Why is hashing important? If you're sitting there trying to steal my password, it's going to steal what is something that has been hashed, but there should exist no reverse map, right? That's how you make sure things are secure. So what has happened is that by hashing it, it took lots of monomers and hashed it all into one bit. If I went backward, it went into several different monomer structures. So in terms of doing a design, it's awful. So in fact, if it turns out for one particular hash sequence, if you picked a number, it corresponded to all of these different structures. Everybody understanding what I said? Or have I lost you? Greg, you look confused. You got it? So this might explain to you why I got away with it, right? Because if there's 10,000 monomers that I haven't seen before, maybe when I take the monomer structure I haven't seen before and hash it, it goes into a bit that I've seen before. So I'm producing garbage, but it's apparently good garbage. Following? So this is the problem with machine learning. When you use somebody else's algorithm, you don't know what the hell you're doing, right? And so this idea that allowed us to get good data actually gave me garbage because all of these different monomer sequences got mapped into the same hash bit. So the X vector corresponds to all of these, and all of these apparently have the same permeability. So I have no idea why this technique works, but it works beautifully. You're looking at me like I'm talking Swahili. You're fine. It's just the way yeah, you got it, right? So this tells me I have to have uniqueness going both ways, right? And so by doing uniqueness, what this technique allowed me to do is look not only at the carbon, but the way the carbon was connected all, in various distances away. So it had very accurate information about connectivity, but because of hashing, I created garbage. So I have to do another way of doing this thing where I maintain the structure uniquely, and that's a technique called max keys. So what max keys does is if you look at this monomer, it tells me I have a benzene ring, that's one here. I have this oxychloride that maps in here, but it maintains chemical fidelity, but it doesn't tell you how things are connected. Okay, so I sacrifice connectivity within a monomer to maintain chemical fidelity. That also is a way of mapping monomer structure into that X vector. Works beautifully, but I've lost information about how things are connected, okay? But once you do that, you can start to do the machine learning. It does exactly as well as before, but now I can start to do things like inverse design. I can also start to ask which features of the monomer are correlated with high permeability or low permeability, okay? Yeah, you had a question.
Find algorithm. Like, is there information about that algorithm that would have told you already?
Yeah. Apparently, I mean, this is why you're not an expert, right? There's a freaking website. This Andrew White guy, and he's got a blog going on. People writing to him saying, I'm getting a ton of fingerprint collisions. Fingerprint collisions are when two fingerprints get mapped in the same part. Apparently, these very well known. It's just you and I, as physical scientists, have no knowledge of that. And so you find out extremely painfully how to rediscover the wheel. And this is why I mean by saying we are users, we are not creators. Okay? Rupert is still happy. Cool. How am I doing for time, Greg? When should I get done? I have time, okay. You never say that to a professor, right? Okay. Okay. Quickly backtrack. You're done in 5 minutes. Yeah, this is group contributions on steroids. That's all it is. I mean, so what I'm doing is, you guys are too young to know about this. There was a guy called Van Crevelen who wrote a book on this, right? But basically what I'm doing at every point, if you give me a new data point, I put it back and I relearn the weightage. So the W transpose basically is the group contribution, right? So I'm training it every time you give me new data. It's basically group contribution. So now we start to say, which feature is correlated with hypermeability, right? And there are many ways to do that. The particular one we use here is called SHAP, or it's called permeability. So the way it works, imagine this is some fingerprint vector. You hold one fingerprint constant, you flip everything else around, and you ask which one affects the permeability the most. So if I hold this one thing, and if I change all of the others and it doesn't affect the permeability, that tells me that's really important. On the other hand, if I flip this one alone, if the permeability changes a lot, again, it tells me that's the guy that has the maximum value in the permeability. So it's just playing games, asking which one of the bits affects the permeability the most, and then you can go back and start to identify which part of the monomer sequence matters the most for permeability, okay? It's a really stupid way of doing it, but that's the way chemical engineers work, all right? But when you do that, you get the same result. So here is a series of gases. Here's different machine learning algorithms. Every time we ran it, this feature size, number 99, was the one that was correlated with the highest permeability always. You go look at it, that's this sequence, C double bond C. So we found out if the backbone is really inflexible, you get high permeability. This is what people are finding empirically in the community, and we verified that. Now, the second most important one is 141, which is a methyl group. That says here, if I put methyl as a side group, that makes the whole thing stiff and also bulky. That makes the chains pack badly, which means the sieve is looser, I get high permeability. All completely intuitive, but now machine learning came back and told me this same intuitive result after lots of blood, sweat, and tears, okay? Here, the technique doesn't work so well. You're laughing at me. I know a lot of people do that. Why are you laughing? Yeah. Yeah, it's not good. I mean, that tells you in the hands of an amateur, best you can do is reproduce what's already known. All right? I will do better. So at this point, it's a very nice modeling tool. But the problem is we don't know what the hell we're doing. A lot of it's just playing games where we don't understand. And things like hashing, uniqueness of going back and forth, these very simple tools that we should have already known because we didn't know, it's become very complicated. At the end of this, if you do it properly, you get results that are sort of intuitive. It tells you the monomer backbone structure is really important. The more stiff it is, the more badly it packs, the better the permeability. It's all intuitive. All right. So this is very unsatisfying. And this is the way people do machine learning today, okay? And so we said, let's pick a different problem where we don't know what the hell's going on. Nobody has any intuition. And now can we see whether we can learn something, all right? So this is a problem that's very close to my heart. And this is how you create nanocomposites, right? And the classic example of a nanocomposite is a rubber tire. That's a rubber network, and you put in carbon black, you put silica particles in there, and the way these things disperse through the matrix is very important to properties. That's very well known. So now we were playing with nanocomposites for many, many years, and we saw this extremely weird result that everybody in the community knows. They say, yeah, we all know about it, but you ask why, and nobody knows why, okay? So let me describe the experiment. You take a particle, a polymer. Particles are generally hydrophilic. Polymers are generally hydrophobic. That's like oil and water. It's like a bad marriage. They don't want to mix. All right? How do you make a mix? You bring in a therapist. In this case, the therapist is a solvent. Okay, a common solvent. You take particle, polymer, put in a common solvent, they mix, you cast, you evaporate the solvent quickly away, and you get a composite. Now, what's weird, you take the same polymer, poly-2-vinyl pyridine, and silica, which is 15 nanometers. Depending on the solvent I used, I get completely different dispersion states. So if I use methyl ethyl ketone, I mix everything in methyl ethyl ketone. It's a common solvent. It's happily dispersed. I cast, I dry the MEK off. This is a TEM picture, beautiful particle dispersion. I dissolve it in pyridine, which is another common solvent, cast dry. Particles are completely agglomerated. Now I can anneal the crap out of this guy. This will never go there. That will never go here. Okay? So the structure of how I come out of a solvent affects the particle dispersion and therefore properties. And I want to understand what it is about the solvent that leaves me the structure. Everybody knows it, nobody understands it. Right? So you go start asking questions, and the number of things that can be affecting this problem is huge. So let me walk you through the variables here. The particle itself, you don't know the chemistry of the particle, you don't know its size, you don't know its concentration. That's 3 variables. The polymer, you don't know its molecular weight, you don't know its chemistry, so that's 5 variables. You don't know the temperature. You have particle-polymer solvent, so it's particle-polymer interaction, polymer-solvent interaction, and what is the first one I said? Particle-polymer, particle-solvent, polymer-solvent, right? So there's about 15 variables. In this case, I've sketched, I think, 3, 5, 6, 7, 8, 9 variables, right? About 9 variables here that could potentially affect the answer. And I want to know which one is driving the problem, all right? And the particles they are charged as well, so there's another variable. So I've said 8 or 9 variables here. And here, you really don't know what the hell you're doing. And we want to understand what the control variables are here. Anybody have guesses what might be important? Ben, you look at you, you're ready to hazard a guess. Play with the chi parameters, that's a good thought. Any other thoughts? The conventional wisdom is chi parameter, all of them. This guy is a smart ass, man. What is this? I mean, yeah, all of them might, right? But I want to know which is the most important. What's the hierarchy? And the general accepted wisdom in the community is the chi parameters, the interaction parameters, right? So we said, let's go figure it out. Let's find out what the data tells us, all right? So when I wrote this proposal to the National Science Foundation, I said, there's an order 3,000 papers on the dispersion of particles in polymers coming out of solvent. I exaggerate, there's not 3,000 papers, there's only 2,000 papers. So my poor student went and scoured the literature, 2,000 papers. Took him a year to do it, and I cursed and swore, right? You can see a pattern emerging here, right? Turns out there's only 15 papers with useful data. There's only 60 data points which use electron microscopy to tell you the dispersion state. So we're extraordinarily data limited, all right? And it turns out people only report samples with well-dispersed particles. Because if it's poorly dispersed, who cares? That's a bad sample, you don't report that, right? So these are the biases with which we started. So you have well-dispersed, poorly dispersed, and you want to correlate across those 15 properties. It's basically a classification problem. To do that, the easiest way to do it is what's called support vector. What you're trying to do is take the data in this very complicated 13-dimensional space, and you want to draw a plane which separates the data into 2, well-dispersed versus poorly dispersed. And you're trying to find that plane, W transpose, that separates the data into 2 planes, all right? So we do that analysis across this 60 data points and 13 variables. Everybody following along what I've done? You seem confused. You're happy. Okay, you're not happy. I wouldn't go that far. Okay. So this is what, yeah. Yeah. No, just classifying 0, 1.
Good or bad?
Yeah, I mean, let's just learn how to stand up, right? We don't want to start running marathons before we can stand up, right? So this is how the algorithm does the support vector, right? So let's pick this one. This is this interaction parameter between polymer and nanoparticle. This is some measure of the electrostatic charge on the particle. This is the Beerem length, okay? The blue points are where we get well dispersed. The red points are experimentally where they are poorly dispersed, all right? Doesn't matter. The machine learning predicts this region in red is poorly dispersed. The region in blue is well dispersed. And you can see it's complete garbage. The prediction tells you should be all poorly dispersed. You get well dispersed particles here. Here, everything should be well dispersed. I'm getting both poorly and well dispersed particles. So I've got no ability to classify the data. You can try other variables. Here it's the entanglement, number of entanglements per chain. We tried every variable you could think of. Again, garbage. All right? So at this point, there's no ability to understand anything about the system and what role the solvent is playing. That's the basic message. So I told my student, write up this paper and graduate and get out of here because we have a non-result. This is completely unpublishable, right? The student came back to me and said, no. There's a problem here because we're collecting data from the literature. Let's go collect our own data. And I'm like, okay, this is good money after bad, but let's do it. So this kid is actually smart. He hired a summer student last summer, and they came up with one particle. They fixed the particle. They picked one polymer, keeping things constant. But basically, they then said, rather than just do one polymer, let me do 8 different polymers, 10 different solvents, okay? And use this as a way of generating data. So you take the different solvents, different polymers, one kind of particle, do exactly the same technique every single time, cast, dry, and then characterize. So you can do transmission electron microscopy. You can see that is well dispersed. An easier technique, which Greg will tell you, is to do X-ray scattering. Intensity is a function of wave vector. If you go down at low Q, large length scales, if it's completely well dispersed, data should be flat. As the slope comes up, it tells you the particles are agglomerated. So it turns out from our examination of various electron microscopy images, if that slope is smaller than about 1.5, the particles are well dispersed. If it's larger, it's poorly dispersed. So I can show you images of that, like that. This is well dispersed, and that is poorly dispersed. I have data using TEM. This is exactly the same system as polymethyl methacrylate, and the particles using ethyl acetate in this case versus acetonitrile, completely different dispersion. So we said, now we have 120 data points, 80 of us ours, 60 from the literature. That sums up to 140. Let me try and throw the data together and see if I can classify better. Still nothing. This is some random polymer-solvent interaction parameter, the size of the polymer. Again, you see red and blue appear everywhere. No ability to classify. Okay, this is literature data and our data together. So then my student said, let's throw away the literature data, look at only our data. And when you do that, suddenly now everything classifies beautifully. So this tells me literature data is crappy. Number one, so take that away. Our data rules. Our data is great. All right? But how did I come up with these two parameters? It tells me the solvent dielectric constant and the polymer solvent interaction parameter are the two most important parameters. What this tells me, if I chose those two variables, I can classify, right? But this is random stuff we just pulled out of a hat. Is there real physics to be governed here? So now we're going to do something even deeper, and this is the new stuff. This is really important. So what you do is, you say, I'm going to do something called a logistic regression. So X is my variable, which has all those different 13 variables that describe every system. This quantity theta is the matrix that goes from a space of those variables to the dispersion state. And so you're trying to find elements of theta. Okay, that's the same old problem. So I'm trying to find this quantity which minimizes the error, but I'm going to put something that looks like regularization. You remember I showed that regularization idea before? Everybody still remember that? You remember that, Greg?
Yes.
Okay. But now I'm going to treat this quantity, earlier on the way that quantity lambda existed in front of the regularization, I obtained that by an optimization. Here I'm going to treat this as a parameter, and I'm going to vary the parameter. This is called hyperparameter optimization. Let's think about it. If alpha is very large, that tells me that any non-zero value of theta is going to be penalized. So it tells me it's going to say theta has no value. It's a whole matrix of zeros. Okay? So then this dominates when alpha is very large. When alpha goes to 0, this doesn't matter. All the quantities come in, all the inputs come in, and then I can't tell anyway which one is important, which one is not. All parameters are important. But in between, as I vary alpha, more and more parameters will kick in, and I can find an optimum. Have I lost you all? Am I still making sense? I'm going to show that to you graphically. So this is like the coolest part of my talk, and then I will be done, right? I have 10 minutes to finish up? Yeah. All right. So I'm varying this quantity alpha, hyperparameter. This black line here tells me how many elements of theta are non-zero. The blue line is for every value of alpha, what is the accuracy of fitting to a test set? So I took my data, 80% test, 20% validation, right? So the blue line is how well I can fit to that data with that value of alpha. And then this one is what I do for the remaining 20%, the validation set. So let's walk here. When alpha is very large, I have no parameters. I'm not doing any regression. And I get nothing. As I reduce alpha, more and more parameters kick in. I'm starting to improve how well I fit to the data. But when I go below this value in this dashed line, you can see the training set gets better and better, but the validation set drops off. So it tells me when I put too many parameters in, I'm doing a good job in fitting the data, but it can't interpolate properly because the curve is getting really curvy. Okay? So at this point, when I'm going through the maximum, is the optimum. So it tells you with the amount of data I have, this is the optimum value of alpha. And at that point, I need only 2 parameters to describe all of my data. Only 2 parameters are non-zero. Yeah?
Alpha doesn't go from 0 to 1. It goes from very big.
Alpha goes from very big to very small. It depends. So it turns out there's a complete analog in a Lagrangian optimization problem with constraint optimization problems. And so when you put a constraint, this basically translates into a value of the constraint for each of the variables. So that's what it's telling you. Alpha depends on the problem itself. It's a positive number is all that's required. If I made sure everything went 0 to 1, all my independent variables also went 0 to 1, then alpha will be from 0 to 1, but I'm not doing that, and therefore alpha can be any real number, all right? So this then tells me that, I have 100 data points, and for that particular case, only 2 variables describe the data. If I had only 10 data points, then maybe the peak would have happened here. I would have gotten only the most important data point. As I add more and more data, presumably I'll start to get more and more parameters kicking in. And so this tells me in a progressive way, I can start telling you which parameter matters the most for controlling particle dispersion, the second, the third, the fourth, and so on. Okay? So this tells me I'm not constrained by the amount of data. The more data I have, the more information I can draw from the system. But at the level of information I have, which is 80 or 100 data points, I can tell you the 2 most important variables, all right? And those 2 most important variables turn out to be the dielectric constant of the solvent and the polymer nanoparticle interaction parameter, okay? That's what the model tells us. It tells us here I should be poorly dispersed, there I should be well dispersed. You can see here most of the data classifies very well. There are some outliers sitting in here, but I'm doing better than anything I've got up to this point. This tells me 2 data points are not enough. 2 variables are not enough. I presumably need more. But at this level of approximation, I'm doing really, really well.
Charge effects.
So yeah, so I'm going to talk about it in a moment, right? So imagine if the particles are charged, right? If I have a high dielectric constant medium, the particle charge is high. So now particle charge being high means the particles repel each other. I get steric stabilization, right? So therefore, that's why when lambda gets very small here, you can see I'm doing a lot of well-dispersed states. And the poorly dispersed states happen for large lambda. Here, the particle polymer interaction parameter matters. So it tells me the most important thing is the dielectric constant of the solvent. That tells me how charged the particles are. That's the dominant variable. The second most important variable is the polymer nanoparticle interaction parameter. So it even tells you sequentially which is most important. This is in a solution. It's in a solution, yeah? So it's now telling me the most important thing. So from that, I can start to derive information about the physics of the problem, right? Yeah.
When it's in solution,
Things are in solution is what determines the final state.
you're saying they're already clustered.
Yeah, exactly. Exactly. Yeah, sure. Speak louder, please. Yeah. Oh, sure. Be my guest. Nothing. I mean, as long as the parameter can be quantified, I can throw it in there. And basically it's telling you, it's saying which one matters the most, which one affects the answer the most. Right, so I gave it 8 parameters. I could have given it 37. This would still pick out the dielectric constant of the solvent as the most important variable because that has the largest effect on 0 versus 1, particle dispersion. The second most important is the polymer nanoparticle interaction parameter. That's what it comes out for me because presumably that has the biggest effect on the dispersion state. So if you put in some irrelevant quantity, it would never kick in. It would be the least important, so you'd have to get a gazillion data points, and you would still not get that point showing up with a non-zero theta value. So this, so it tells you I can put in whatever irrelevant crap information I want. This will only pick out the ones that affect the answer the most. No. So you're thinking about this all wrong. The hard part is doing the experiment. Because every experiment takes 2 days. But this 80 data points took a summer student the whole summer. So they spent 10 weeks in my lab. So we're getting 2 data points a day. So that means on average, we're spending 4 hours per data point. Collecting 20 pieces of information for every system is a literature search, which takes 5 minutes. So I would say be completely agnostic, bring in the phase of the moon, talk about whatever you want, whatever you can find about that system, you input that. If it's relevant, the algorithm will pick it up. So it's actually very powerful because it's telling you it doesn't matter what I care, the algorithm will tell me if it affects the answer. If it does, it's important. If it's not, it'll automatically tell me theta is 0 for that variable. You have a question?
Got the answer. Kind of question. Start with one parameter, iterate, add a second one, third one, fourth. You kind of have to look for it. Like you kind of know some of the parameters that might affect this type of dispersion. But let's say if you're blind to it, you just keep going to figure out.
No. What I would do is if you have a system, you take every known physical property of that system and you put it in there. Presumably you set up a database like Procter & Gamble has, which has everything about that system. You throw that into this algorithm and it'll go out and pick out the most important, the second most important for that particular property. So the more things you can tell me about the system, the more well I can distinguish the physics. But if you don't tell me that, I'll find out that the parameters I have are not doing a good job. So if I don't have the relevant parameter to tell me I'm not doing a very good job, so I need to go look for something else. All right. So it'll tell you so if you can't do a hyperplane division, you didn't pick the right data set of input variable, right?
You had said that the 60 data points in the literature were garbage. Did
I
you
didn't.
Did you try and go back and use this classifier scheme?
No, nothing.
That?
Still garbage. Still garbage. And the reality is that your test set keeps going up. The training set never changes, completely flat. So it's telling me, even though I can do anything I want with the test set, the training set, right? On the test set, I have no ability to interpolate. So it tells me there's something fundamentally wrong with the literature data. So it doesn't work. We went back and double checked that just to make sure that with this knowledge, maybe there's still something to extract from the literature data, but apparently not. Here, protocols really, really matter. Somebody asked me about protocols. You asked me, I think somebody back there asked me about protocols. Protocols matter here a lot, right? I should shut up. I think we are out of time. So let me quit. They have other parts of the story. You can derive, once you know what the variables are important, I'm a physicist, so I can go figure out what the physics is. So machine learning doesn't teach you about physics, but it tells you about the variables. Once you know what the variables are, you can make physics models. So that's the next big step we are doing here. I'm not going to talk about that. Let me wrap up. The data is the most important thing, especially in these things where we have such limited data. Do not use literature data unless you know exactly the protocols used. One thing people love to do is they take literature data and augment it with simulation. Please, for heaven's sake, don't do that because they are just completely different things. And here I've just taken data from experiments of different people, and that gives me garbage. If I use a protocol, which is a simulation with force fields that came from I don't know where, I don't know what the hell I'm doing. So this is a very powerful way of saying, be extraordinarily careful about the data you use. There's this idea of using FAIR principles, which says, they must have well-documented ways of doing it, follow certain protocol. That's really important. You have to tabulate data that are both good and bad. We never, as academics, do bad data because all our data is good. So these are sort of very important things that we have to change if machine learning is going to be a part of our community. But if you do it right, it can actually start telling you something about the physics underneath there. This optimization idea that I'm telling you is new to the field. It's taught me a lot. And again, there's so many more tools in the machine learning community. If I learn all of those, I think we can have a huge impact. But we need to have this conversation between computer scientists and physical scientists. That doesn't exist at the moment. Guys, this is amazing. None of you guys went to sleep, and I've been talking for an hour. Before you guys go to sleep, I'm going to quit. Thank you so much, Greg. Thanks, Peter. My pleasure. If you have questions. I have exhausted people, I feel. Okay, fantastic. Peter?
Yeah, so we're gonna present the lectures and awards, this and that, and then Gerard Taylor is gonna say something. Example after that, and I think that we have different speakers.
So Sanat, thank you for coming out here today and presenting this lecture. This is to recognize you coming out here and awarding you the lectureship for 2025 for the P&G Soft Matter Symposium here at the University of Cincinnati. Thanks for your coming out here and presenting a great lecture to us.
Thank you so much.
Thank you. Appreciate it.
Morning.
Well done.
I would be amiss, so I'm the person standing here today. I would be amiss not recognizing Ajay Muralidharan, who unfortunately is not able to join us here today in the room. He did a lot of the legwork and hard work in organizing all of this together with Greg. And I just get to be the person who stands up here and recognizes Sumant. Thank you. Thanks, Peter.
Thank you. Greg, should I follow? Very good. I took the microphone because we have people online, and I recognize some scientists from Procter & Gamble in microscopy, imaging, and thank you for doing that. So congratulations for your award. Congratulations also for challenging us today, at least part of the industry. This is really eye-opening. And I would like to congratulate all of you who have made a very wise decision. I do believe there is only wise people today, except me. But you made a very wise decision to come today to attend a lecture on soft matter, especially the one that you delivered. And I will elaborate a bit further. Whether you are students, undergraduate, PhDs, having already succeeded, or people from the industry, I see a lot of Procter & Gamble or faculty, I think you made a wise decision. It's Friday afternoon, there are many temptations, and I'm glad you came here. I'm glad I came here. So I'm a senior R&D vice president in Procter & Gamble. What does it mean? It means that I'm the least competent in science in the room and remotely. I'm a businessman. And I do believe that P&G has made a wise decision by sponsoring lectureship on soft matters and being able to stimulate our scientists here and remotely to attend your talk. Why is that? So I will indulge a bit on Procter & Gamble, but it will be true for the food industry. It will be true for the energy and oil industry. Soft matters matter. Let us say for Procter & Gamble, we have been in business for 188 years, if my math are correct. 188 years. There are very few companies that have survived 188 years and are still thriving. And there are two reasons for that. It's not marketing, it's not media, it's all about the consumers, and it's all about the science. The consumers, we have to delight them, we have to understand them. And you know, consumers are made of soft matters. Consumers are sleeping on soft matters, hopefully, otherwise they don't sleep. Consumers are washing themselves, putting makeup, washing their laundry. using Puffs, Bounty, and Charmin, who are pure, the most complicated soft matters. I have Lisa Sanchez, Vice President, Family Care, Procter & Gamble. It's all about soft matters. They touch, they live. When they repair their home or they get their home built, they do plasters, they do cements, you name it, it's all about soft matters. So that's one thing, it matters for the quality of life of people. Second paragraph, the science is underdeveloped compared to other things. Talk about small molecules, talk about organic chemistry and reactivity, even talk to me about human genome and the DNA, RNA, and lipidomics. I think the science is pretty well advanced for good reasons. Soft matters is this full of mysteries. I would have loved Professor Dejean to meet you. I know it does not happen, but I could imagine you in the same rooms, what you will have discussed about, because in his Nobel Prize address in 1991, I was born in France, so I have a kind of soft spot with Dejean because he has been one of the fellows who has made me wanted to go into chemistry, and I ended up in Procter & Gamble because I was not as good as him probably. But you know, he made this little because he was declaring soft matters as one of the area of science that is understood. Now, he was a physicist. He saw it through the lenses of physics. I'm right today that you are bringing it through the interdisciplinary role because it's one of the field of science that we do not understand very well. And why does it matter in Procter & Gamble? Because it's very simple. To be successful, not only you need to create products that delight the consumers, but you have better to understand how they work, how they are made at the molecular level. Because every time we don't understand that, we leave ourselves, how to say, subject to surprises. Surprises can be simply that the quality of a batch that we receive today in our manufacturing is not as good as we would have liked it to be. Surprises is because there are some supply chain disruption due to geopolitical or just the reasons. That's part of the industry. And you can face these surprises if you understand the science. The more you understand the science, the more you can be bold, you can be daring, and you can make decisions that are not lottery, because we are in a business that needs to last for 188 years, so science matters. This is why soft matters matter to us, because it keeps us awake at night. Right, Lisa? I mean, in all your business, we are still having to build on empirical models, but we don't understand the why. And if we understand the why, you brought it to life very nicely, then we can make rational decisions. And even better, we can start to see the things that could work better than today. So I'm just saying, you know, this is a very soft matters, is a really wise field, and you are wise to attend today. Hopefully to have enjoyed, like all of us. I mean, I have never seen as many questions in a lectureship on a Friday afternoon as today, which speaks volumes. So keep attention. You have really found a field, whether you want to continue in academia or whether you are wondering what is it you can deliver for the industry. We love soft matters. Even if we don't understand it, that's why we love it, because there are plenty of things to understand. So thank you again and congratulations for this amazing talk and of course for your awards. We hope to see you more into ACS and all the other things. Okay, and put notions, you know, I mean, if Dejean and you were in the same room, I could dream about the kind of intellectual conversation you will have, because you are bringing totally the new angle. Thanks to machine learning, we can start to have new hypotheses. And you say it well, that was, I was waiting for the second paragraph. It's okay to have some models emerging from machine learning, but you ask, why does it work like that? Which is always in the industry, we love to have an assumptions, but we like to understand why did it work like that? Explain to me how this magnificent algorithm will work for us. I'm turning to the P&G people. You could imagine that when the first example told me, you told that molecular weight don't matter, crystallinity does not matter, it's only the monomer. I was just saying how many of our problems could be solved if it were that simple, that we find this magic parameter that can predict the thing. So again, thank you very much and great use of your time. And I look forward on the posters to see what questions, especially from the students, you know, emerge out of that. But again, congratulations, okay? And I'm amazed of how, after all your trip from India at 100 degrees Fahrenheit and trying to find your flight, you are such a bundle of energy. So very.
Thanks. So we have two more speakers, slightly shorter talks, but Matt Barker from Procter & Gamble's and Ajay Muralidharan, try to do that right. Muralidharan, right? Murali, I guess, means flute in Hindi or something there. But anyway, they're also involved in the machine learning business. So Matt's going to talk about leveraging deep learning and large language models for chemical discovery at Procter & Gamble. Matt's got a PhD from University of Kentucky, and then he's been at Procter & Gamble for 20 years, I think. And then
Almost 25.
or almost 25. Okay, so he's a senior director fellow in research and development. So I imagine that's important. But and then so he's and then AJ's a younger PhD from Tulane and also working in the same area. So let's welcome Matt to.
Can you flip to the other one? Hopefully you guys can still hear me online. Yeah, it's just the web page. We'll use the PDF. No, the Chrome or the, yeah, there you go.
Okay.
Yeah, George figured out
Okay.
how to
You
do
moved
full
George.
screen. Oh, there it is.
Okay. All right, great.
There we go.
Thanks.
And I might have to stand up here to advance unless you have a clicker. Okay. That's okay. I don't need a pointer. It's fine.
This also advances.
Oh, it advances too. Okay, sure. Yeah, so I'll go ahead and get started here. So, yeah, thanks for the introduction, Greg. Yeah, so we'll talk about AI a little bit. We'll talk about large language models.
This is your printer, and you can advance slides.
Okay. Oh, great. Okay. Yeah, so just very quickly, I think the other piece of background I'll mention is working in the data science area, and my PhD's in statistics. At actual focus was in chemometrics, and actually doing classification problems with chemometric methods back in the late 90s. It wasn't very popular at that time, as you can imagine. But it certainly grew over time, and I've worked on in a number of different areas in P&G, and more recently working with Ajay on applications in chemistry and molecular discovery here. Oops. Oh, sorry, it advances really quickly. And so Ajay, my counterpart here, yeah, while he's been with the company about 2.5 years, comes with more PhD chemical engineering background, molecular simulation theory, a lot of strong programming, but then coming into the company, really started to pick up machine learning methods and with a lot of interest in AI. And so we started working together, and he's done an amazing job. And so he put together a few examples here that we'll talk about. One with small molecule cheminformatics, another one that's polymer informatics, and then we'll talk a little bit, and those are in the area of property prediction. And then we also started looking at large language models and how they could be used to do some of those kinds of problems and for AI agents assistance. And oh, sorry, some of the builds are not working here. Ajay unfortunately is not able to join us due to an injury, but you know, he did a lot of work on these projects, and we really appreciate that. And Gerard already covered all the spaces where P&G is active. You you probably used one of those products today, potentially. But the real focus is on that I'll cover is where chemistry comes into play in some of the chemically formulated products. Sorry, sometimes it clicks and sometimes it doesn't. Okay, so and really a thank you to Professor Kumar who covered the real complexity of these some of these problems in terms of it's not just how do you pick a molecule based on one particular outcome, but there's really a host of different things that you would like to optimize, and then potentially using things like machine learning to do that. And so we look at performance, other areas of human safety and environmental safety. Some of our safety folks are joining us today. Look at things, obviously cost, and the most important things Gerard mentioned were meeting the consumer need. And so all of these things together, and then trying to, in some cases, pull data that's available, but also ideally generate new data and experiments. So it's really it's an iterative learning process. And because of what we found that, this really is a lot of times a small data problem, especially in the polymer space. Thanks to the efforts of some of our senior leaders have put together, this funding and opportunity with some co-industry sponsors, and with National Science Foundation matching those funds 3x to put together a $9.5 million fund for research in sustainable water-soluble polymers. And so they've unfortunately they've already closed the window for proposals, and they're reviewing them now. But we're super excited about this and the potential of cross-industry data and opportunities to work with academia, but also provide data for the broader community to learn from, really. And so a few examples that Ajay and I put together. One around small molecule cheminformatics, and just to give you a flavor of some of the problems that we work on at P&G that are helpful to us. Sorry, this is more of a build with the. I wasn't able to get the PDF, or I got the PDF working. So sorry if there's a lot of information fast as we go through some of these slides. But sort of focusing at the top, you have, we look at the solubility of looking at different solvents, and so one of those measures that we use are Hansen solubility parameters. And what we found is being able to predict these measures in order to understand the similarity of different molecules, and which ones sort of work together better. This is using a method called message passing neural networks that takes a textual representation of the chemical structure using a smile string, and then predicts dispersion, polarity, hydrogen bonding. And a couple of interesting things about this methodology, when you have more data, and in this case we do for small molecules, we had about 1,200 molecules, and we're able to build a deep neural network to look at look graphically at the structure of the molecule to predict these measures. And then you can also, with this method, get an idea of a prediction reliability, basically. And so with the method, we were able to, or with this model, I should say, we were able to predict with higher accuracy than some of the other models we've had in the past. And it uses an open source toolkit called ChemProp. So with some Python programming and a deep learning toolkit like PyTorch, you can start to build these models, and we have an example where we're using it as well. So in this case, screening solvents for skincare actives. This is the Hansen solubility sphere, and in this case, we had an active in the center. And the idea is to use the model to then identify other compounds that could be similar enough, and then the dots here are really the experimental data. So the circles that are closer to the active in this case were ones that were predicted to be versus the X's. And so using a method like this, you can get you can really reduce the amount of resources needed to do a lot of additional experimentation, and actually performs quite well. Let's see. So just want to transition a little bit to the problem of polymer informatics, which is a much more challenging problem. We talked about a lack of data in many cases, and also the difficulty of some other things that you have to consider when you're doing that kind of modeling. And see, you said the bottom is the laser?
Yeah, the bottom.
Yeah, okay. So the example model I showed you before on solubility is really, okay, can you take the structure of a molecule and create a function that maps it to some sort of target property? In polymer informatics, a lot of times, yes, you want to understand that structure somehow, but the processing conditions are important. That's something Professor Kumar covered as well, in order to predict some of those target properties. And my time working in this space isn't that long. I've worked on many applications in deep learning and image analysis and other areas of P&G. And I guess I would say, what I've learned from doing that kind of work is, having the right kind of data that allows you to, understand all the features that are important to do the problem is critical. And here it's like you have so many features, but then just not enough actual data to solve the problem. And so, how can you break this down into smaller pieces? There's some examples of methods for sort of featurizing the chemical structure. One method is P-smiles, which is, again, instead of just using a smile string, you also indicate sort of the ends where there could be repeating units. And it was even shown earlier, some of the limitations of these fingerprinting methods in terms of mapping many to few. And so there's been more recent effort in using things like transformers. These are models that essentially try to understand all the interrelationships between different elements of a long sequence of data. Similar, even ChatGPT, which you've probably heard of, the T in GPT is transformer. So these are widely used type models that can be reapplied to this kind of data where you've got long sequences of information. And then also graph neural networks and graph-based methods. But the other piece that's important is adding in these experimental features, learning which ones matter for a given problem. And so two things we wanted to point out were there's sort of a gap in data sources. One is the top left is around, this is a data source that is available called polyinfo. You can, and a lot of the data is pulled from literature. And one of the challenges, the advantage is yeah, there is some available data, but really the challenge is they don't allow you to scrape that data. You can only get a little bit at a time. And other issues like they're aspects of that data they're not capturing, which they talked about earlier in terms of maybe even some of the processing conditions, so that instead of data that's all sort of consistent, you've got a mix and match of different types of data, all and then trying to build a model with that, you can basically get garbage. So it's still not. I would say it's still not clear, how useful that is just yet. But the other problem is, in some cases, there are synthetic data sets that are created. In this case, Poly1 is another data set which is available for academic use only. And so, for industry groups that would like to make use of some of these data sources, we're not able to. And so we just wanted to share an example of where we're doing this using these methods at P&G. This is an example where we're trying to, basically, if you take a polymer sequence, which, or in this case, like a copolymer, where you can represent each of the SMILE strings, you can featureize them using things like descriptors, geometric, or use RDKit sort of physical properties, and you can create a set of features that represent those strings. And in this case, you can actually combine them together in sort of like a weighted average. And that allows you to featureize some of copolymers and more complex structures. And it's kind of interesting. This similar approach is used when they do formulation modeling as well, when you have multiple ingredients and then you look at mixture and ratios of those. A similar kind of approach in polymers can be used to actually create a model, in this case predicting, we've sort of masked the identity of this example, but I'll at least tell you it's a cleaning product. No big surprise there, P&G. But this is an example of taking a water-soluble polymer and then trying to understand its cleaning efficacy, basically. And so it can be used in some cases. There aren't a lot of processing condition features here, but in harder problems, it's more critical to have something like that. Okay. So I know I'm short on time, so maybe I'll hold questions for the end. I want to switch gears into some of the play that we've had with the language models. So there are two different types of problems we've tried to work on with large language models. One is around molecular property prediction, and the other is using them as sort of assistants or chemistry assistants. And in the first one involves, I'm gonna sort of show you an example here. So a very common data set that's used in the machine learning area is what's called the iris data set. It's a very simple problem. You have 3 different varieties of irises. They have 4 different measurements, and from those you try to classify which of the 3 types. Typically, the way this problem works is you take that input data set, you use one of the methods that Professor Kumar described, and then you use that to like logistic regression, and then you try to predict which category class of iris you have. If you wanted to do this with a large language model, what you typically do is you would take each of these and you sort of create a sentence out of it. And you don't even need all of the data. You need a few representatives of each of those classes. You create a few sentences, and then miraculously, the model actually will, with what's called fine tuning, it will be able to, as you give it new sentences, it'll tell you which variety it is. And so there's a couple of things going on there. One is it's using the knowledge that it's already built up in that model, which allows you to use ideally less data in order to apply it. And so Jablonka et al. From University of Wisconsin-Madison, he put together an approach similar, but doing this with chemical data. And the approach can be used, for classification, or regression, where you have a chemical and you want to understand whether it's high or low, or predict a number. In addition, it can be useful for the inverse problem, which is tell me which structure have these properties. Okay, and so we played with this technique a little bit, and one of the interesting things that we found in the process was, let's say you have a traditional data set in order to solve this problem on the right-hand side, in this case using Mordred descriptors to predict this EACN. You can do it with very high accuracy in some cases, using the large language model, this GPT-Chem. We weren't able to do it quite as accurately, but it does kind of work, which is interesting. This was, in this case, I think they were using GPT-3 as the model to do it. So one of the things that may improve is as the language models get better. So I think the takeaway from this is, if you've got bespoke data, you could probably get your highest accuracy doing it that way. But language models, maybe they're a little bit behind, but are much easier to access, easier to democratize to more people. And so, speaking of democratizing tools, that was one of the things we were really interested in, using creating essentially a virtual assistant using a large language model. And really, within P&G, we have various databases. We have some models that are available. I mentioned one of them, the Hansen solubility parameter. We want to make those as available as possible to chemists, chemical engineers, formulators in the company. And so putting that behind a chat-based interface is of interest. And in this case, we built on a tool called ChemCrow. And Andrew White was mentioned earlier. His lab was actually the developer of this tool. But basically, it uses a language model, but that's more of used as an orchestrator of various tools. And in this case, you have public tools like web search. Think of a calculator, could even be Python programming code, various documents, Wikipedia, and that kind of thing. And in addition, you can tie in your models or data and allow the agent to be able to choose from these different tools depending on the question that's being asked. And so it's sort of a knowledge reasoning based tool. And these types of tools are really starting to become a lot more popular. And LangChain is a popular framework in the computer science area that's being used to do it. And just to add, so these are some of the additional tools that we integrated into it. I mentioned the HSP model, log-P, molar volume, and a few other models that allow us to then combine the functionality together. Yeah, unfortunately, I can't do a full demo because I don't have my PowerPoint, but I've got a few screenshots of how it works. So if you can read that first question, basically, what is it? So you've got a chat interface. You can put in the question. In this case, as an example, we picked what is the most hydrophobic among hexane, benzene, and toluene, and what's the flash point of that result? So basically, what it does is it breaks down that question into the pieces, and then in this case, you've got a chemical name. In order to use some of the models involved, you actually have to have a smile string. So the first tool it'll use is, well, actually, the first thing it does is decide, what does hydrophobic mean? How am I going to measure that? And so then it looks up, I know log-P, so I'm going to go find that. Well, what do I need to get log-P? I need a smile string, So it's sort of taking something that would involve several steps for a human being to have to go through and then do all those steps and then bring it all together. And let's see. So this is just sort of showing you the logic. Luckily, we captured a few of these screenshots. Yeah, sorry I couldn't show you the live demo. But basically, yeah, so here it's getting the smile string and log-P values. And let's see here. I don't know what all. Okay, so yeah, once it determines the log-P values for all of them, and then it determines hexane has the highest one, then it calculates the flash point for hexane, basically. So it's possible with these kinds of tools. They're definitely worth checking out. So in conclusion, I've mentioned LLM-based property prediction. Less accurate than traditional methods, but definitely worth keeping an eye on. The agent-based tools to help democratize data and models and enable researchers to work more efficiently is definitely something that deserves a lot further investigation. And then we're also seeing this even in lab assistants, changing how we can better set up and automate experimentation. And then I think the other thing, we're really interested in supporting is the interdisciplinary nature of this work and cross-industry partnerships and bringing together the different elements of the kind of technology you're seeing plus the scientific discovery. So with that, thank you. Oh, yeah, go ahead.
With the LLM right at the end, the hyperlistening, is there a way to validate that and sort of do an active learning of that, or is that?
Yeah, I mean, one of the things we've been talking about is setting up, designing a series of questions that we could use to do validation, because the language models keep improving, and it's funny, like P&G's access to like GPT-4. We have that because they created an enterprise access, basically. Whereas some companies won't even allow use of it because they're afraid data is going to, escape and whatnot. So our IT folks have worked very hard to give us the kinds of access we feel, is secure and we can use. It is, but pieces of it. So ChemCrow is an open source project. So any of you could download that, and with your GPT API access, you could hook that in. In terms of, there are a number of tools that are already available in ChemCrow, and then you can add whatever tools you think are useful to it. And there's also a lot more, ChemCrow came out maybe about a year and a half, at least a year and a half, maybe 2 years ago now. So there's some emerging agent-based tools that we need to continue to keep an eye on. Yeah. Any other questions? All right. Yeah, thank you.
So we have George Stan.
Oh, do you want to do?
That's all right. It doesn't matter, but yeah. We've got George Stan from chemistry for the UC kind of representative for this, and he got a BS degree in Bucharest, and then in physics, and then went to Penn State and got his PhD in physics in 1999. Were you there then, or? I don't know. Senat was also maybe in the same time at Penn State, and then went to University of Maryland's Institute for Physical Science and Technology and National Institutes of Health. And he studied protein folding and using machine. Now he's published. There was a PNA, Proceeds National Academy of Science paper recently by him about this kind of topic. But so I'll let you. But thanks for coming.
I'd like to start by thanking the organizers for having me here, and thank you for the nice introduction. It gives me a really great pleasure to be at this symposium, especially as as mentioned, I happen to overlap with Dr. Kumar early on in my career at Penn State. I was just starting my PhD at that time, and Dr. Kumar has provided inspiration early on for my career. Today, I'd like to tell you a little bit about the work that is going on in my lab. And this is kind of switching gears in terms of soft matter. Our interest is in protein folding related aspects, particularly in the work of machines, molecular machines that perform, in fact, remodeling of proteins. This is a class of machines called AAA+. We're using molecular dynamics simulations and machine learning approaches for these purposes. So I'm trying to keep it relatively short for this talk, since I know that we are kind of tight on time. So in a nutshell, the protein folding problem involves various aspects. I'm sure that many of you are quite familiar with the success of the AlphaFold approach, which addresses one particular aspect of the question, that is, given a particular sequence of amino acids, what is the structure that the protein adopts? This is a very important question, and it has been a challenge. However, in the cell, there is an additional question that refers to the kinetic process of acquiring this particular structure. One has to recognize that in the cell, the protein has a limited time to adopt the structure that allows it to fold. But also, there are competing processes that can be deleterious, such as misfolding and ultimately irreversible aggregation that can lead to even diseases. So for this reason, the cell has evolved a series of mechanisms that are generally termed as protein quality control mechanisms to address the protein folding problem and assist either with the folding process itself. So this is one branch of the protein quality control mechanism that is handled by chaperonins, or if a decision is made that the protein is not rescuable, then the protein can be destroyed by proteases. And for the purposes of my talk today, I will focus on machines that perform this particular aspect of protein degradation or indeed protein disaggregation. It turns out that these machines, and I should mention that both branches of protein quality control are actually governed by molecular machines. That is, they are using energy in the form of ATP hydrolysis, and they perform remodeling of the substrates. But for the purposes of protein degradation, in fact, there are specialized compartments of the machine that include a motor, which uses ATP hydrolysis as its fuel, and in order to engage the substrate and take it apart, and then the protein is passed on to another compartment that performs the actual cleaving of the polypeptide chain. I'm going to give you an idea of our studies on the motor itself, but it turns out that we are also interested in the process of the cleaving of the polypeptide chain. And in fact, a senior student in my lab, Tarushi Rajaguru, is going to present a poster later on. So I urge you to stop by and learn more about our interests in these machines. So as a sort of an outline, I'm going to briefly discuss the coupling between the chemomechanical mechanisms of the protein degradation or disaggregation. And as such, I will focus on two particular topics. One being what the allosteric communication is within this AAA plus machine, as well as how we are using some machine learning approaches for characterizing the functional states of these machines. So in terms of the aspect of the machine functioning, this generally involves engaging the substrate protein either from one of its termini or from some sort of loose ends, some exposed loops that can be engaged at an opening of the cavity. These machines, in fact, have a donut shape that involve one or two domains that can hydrolyze ATP. So as such, they form either single or double rings. It turns out that there are a set of loops that protrude into this central channel that are quite flexible and are able to engage the substrate via these exposed loops or termini. And these particular loops themselves involve conserved amino acids. So these involve, in fact, interactions via aromatic rings that sort of do a paddling onto the substrate as they engage them and promote, in fact, the unfolding of the substrate or disassembly, and then passing of the disassembled substrate through a narrow pore. This pore itself fluctuates in diameter between about 10 and 20 angstroms as the machine is undergoing conformational changes. So all of these machine mechanisms are ATP dependent. So these involve ATP hydrolysis, and the central pore loops are able to promote the unfolding and translocation of the substrate. I would mention that this is a sequential allosteric mechanism, meaning that, in fact, the machine, which typically involves 6 different chains, will not operate in concert, but it will operate via sequential mechanisms of each of the protomers. A remarkable aspect about this family, which is called the AAA plus family, so these are ATPases that are associated with various cellular activities, is that they are able to promote their remodeling action onto substrates at very different length scales. So we are particularly interested in protein degradation. These are governed in bacteria by the CLIP machine, so caseolytic proteases, which can be CLIP A, CLIP X, CLIP B, and so on, CLIP Y. The proteasome for the human version, protein disaggregation for HSP104 or CLIP B, but also remarkably microtubule severing, which involves in fact severing microtubules, which are very long polymers, which are in fact 3 or 4 orders of magnitude longer than a typical globular protein. So it is remarkable that these machines are able in fact to promote their action via this basic mechanism of using ATP hydrolysis as a fuel, applying mechanical force repeatedly onto a substrate, and then performing either protein degradation or disaggregation, or indeed microtubule severing. Recently, it turns out that the number of structural studies highlighted that these hexamers adopt not a planar structure, but typically a spiral structure. So this is somewhat unusual because one would expect that the protomers would align in registry, but in fact, they are aligned in a spiral. So this, in fact, raises questions about how the mechanism works. One proposal is that there is a sort of a hand-over-hand mechanism, meaning that each of these protomers is able to apply mechanical force in turn onto the substrate. And by applying this in a sequence and in the spiral, essentially this would work in a hand-over-hand type fashion. And this has been characterized by means of various experiments. It turns out that this would correspond to promoting about 2 amino acids per each ATP hydrolysis event into the pore, with a translocation that would end up being about 12 amino acids per second. In more recent experiments, in fact, a different proposal has been made of a Brownian ratcheting type mechanism, which in fact was the result of recent experiments on optical tweezers or single molecule FRET studies that involve in fact a very rapid translocation mechanism. I should mention that for the hand-over-hand mechanism, in fact, this suggests that there is a translocation that is based on ATP hydrolysis. However, in these more recent experiments, it turns out that there is an ultra-fast translocation of the substrate, even on faster timescales than ATP hydrolysis. So in fact, the estimates here are that about 14 to 28 amino acids can be promoted per burst. And then the translocation can be, in fact, even 1 or 2 orders of magnitude faster than the one that would correspond to the hand-over-hand mechanism. So the question is how these mechanisms work and whether we can understand, in fact, the machine works for this particular machine. So our approaches are to perform molecular dynamics simulations on these machines. I'm going to focus for the purposes of today's talk on just the allosteric mechanism, that is the coupling between the ATP hydrolysis and the conformational changes of the machine that underlie the unfolding and translocation of the substrate. And in fact, since I'm fortunate that my wife and colleague here, Ruxandra Dima, is interested in microtubule severing machines, this afforded us the opportunity to compare and contrast the mechanisms for the AAA plus machines involved in protein unfolding and disaggregation, as well as in microtubule severing. I will mostly discuss the results on protein disaggregation for the purposes of my talk. But let me note that microtubule severing machines, in fact, share a similar structure to one of the rings of the protein disaggregation machines, such as CLIP B. So our approach is to perform simulations. We are using the GROMACS program for that. We extend this as far as we can for molecular dynamics simulation. So 9 microseconds is kind of a state of the art for such involved simulations involving completely solvated systems and fully atomistic. And we typically perform simulations for pre and post hydrolysis states of this machine that may be in complex with a minimal substrate. So these typically have to be performed on supercomputers. So we use, in fact, allocations at supercomputer centers such as the Pittsburgh one. So in one set of studies, we noted that the structural aspects of highlighted in cryo-EM studies, which highlighted that there is a network of salt bridges that are present in the between the pore loops, are in fact persistent even on the simulation timescales. But we also note that there are additional salt bridges that dynamically are important for the NBD1 domain. However, for the second nucleotide binding domain, in fact, there are fewer such salt bridges. And this allows us, in fact, to suggest a mechanism in which the loops themselves collaborate during each particular cycle. So in fact, this would involve passing of the substrate between the subunits themselves. By examining the fluctuations, the conformational fluctuations for each amino acids, we can, for example, look at the cross correlation between different amino acids, and that can be used to build a network of such correlations. And one can cluster these results to obtain a networking of all of the amino acids in the structure. So this highlights, in fact, for the nucleotide binding domain 1, there is a particular coupling between the large subdomain of the NBD1 domain and the small subdomain of a neighboring protomer. So this is interesting that throughout the NBD1 ring, in fact, there is such coupling between protomers, which suggests that there is communication around the ring via this type of coupling. In the other nucleotide binding domain, it turns out that there is mostly intraprotomer coupling. So the colors are in fact coding the particular coupling between the regions of each protomer. It turns out that there is mostly intraprotomer coupling, except for the particular loops that protrude into the central channel. So this suggests that the loops themselves work in a more cooperative fashion within the nucleotide binding domain 2. By comparison to the severing proteins, it turns out that for the severing proteins, again, these have homology with NBD1. Nevertheless, for them, it turns out that there is mostly intraprotomer coupling, suggesting that there are very different mechanisms of action, even when there is strong homology. One other question we asked was about the fluctuations of the pore loops themselves. So for these purposes, we approached the autocorrelation function of the distance between the pore loop 1 and the central residue of the pore loop 1 and the center of mass of the chain. So we used, in fact, a theory that allows us to use a scaling approach to understand the fluctuations of the pore loops and to relate them to longer timescales that are available in experiments. So in fact, we have probed such timescales over the duration of our simulations and compared them with experiments that have been performed by our collaborator Gilad Haran at Weizmann on the timescales that are accessible in experiments. So it turns out that our simulations predict a mean relaxation time of about 30 milliseconds over the SM-FRET observation timescale of 1 millisecond. So that compares favorably with the experimental one at 43 milliseconds, again, based on the extrapolation that we can do using the scaling law. So it turns out that this mean relaxation time lies between the fast and the slow times, which suggests that there is a substantial coupling between the collective and the local motions. Another question that we asked was, what is the allosteric communication, that is long-distance communication between the ATP binding site where hydrolysis takes place and the pore loops, which themselves perform the mechanical action? So for these purposes, we perform simulations that involve both the wild type machine and the mutated machine, where the mutation, in fact, hinders ATP hydrolysis. So this is a so-called BB mutant because it abolishes ATP hydrolysis in both nucleotide binding domains of the machine. This is inspired by experiments that have been performed by our collaborator Gilad Haran, which highlighted through SM-FRET experiments that the pore loops have a differential response to ATP hydrolysis abolition. So whereas in the case of the BB mutations for pore loop 1, there is a weak perturbation of the FRET efficiency, as noted here. There is, in fact, a strong overlap between the FRET distributions with or without ATP hydrolysis. For the other pore loops, pore loop 2 and pore loop 3, there is, in fact, a shifting of the SM-FRET distributions. So this suggests that there is a differential response of the pore loops, and perhaps this suggests a mechanism that pore loop 1 can act independent of ATP hydrolysis. Our approach was to use a graph theory network, graph theory-based approach based on our simulations. So we constructed, in fact, a cross-correlation matrix for all of the amino acids, and then we inferred an allosteric network based on the coupling between neighboring amino acids. So this is, in fact, a theory that has been proposed by many labs. This suggests coarse graining of the protein structure itself using nodes at the C-alpha position, and then interpret as network edges the distances between neighboring amino acids up to some distance, and using the strength of their coupling, using their directional correlation network as the weights for these network edges. So one can then identify so-called optimal paths, which are the shortest paths between two distinct amino acids, or suboptimal ones, which are somewhat longer paths that can take some detour between the two. It turns out that the optimal paths are not the ones that are perturbed the most upon some mutation or perturbation of the structure, but the suboptimal ones are more informative. So by comparing the network paths, the set of network paths, optimal and suboptimal for each of these pore loops, it turns out that for pore loop 1, we noted a strong overlap between the network paths for the wild type and for the BB mutant, whereas for both pore loop 2 and pore loop 3, there is a strong perturbation of the optimal and suboptimal paths. So this is consistent with experimental observation that, in fact, the pore loop 1 might be less dependent on ATP hydrolysis, and supports the hypothesis that, in fact, ATP hydrolysis may not be the only mechanism for the unfolding and translocation. And the sort of a final story to my discussion, I'd like to highlight how we use machine learning to try to understand some of the features of this machine. So for these purposes, we are breaking down the machine into structural elements. Generally, we refer to secondary structural elements such as helices. For beta sheets, we further break them down into individual strands as well as loops. And for this particular study, we have used, in fact, two particular descriptors, which are the solvent accessible surface area of the residues of one particular structural element, or the Coulomb interaction for that structural element with respect to the rest of the protein. And again, we're doing a collaboration with the DEMA lab in order to try to understand the differences and similarities between microtubule severing machines as well as disaggregation machines. So for these purposes, we are considering a structure of the machine that involves binding to ATP as well as a substrate. By removing each of these ligands, in fact, we are able to perturb that structure and understand how each of the features contributes to this structural description. So for these purposes, we are employing multi-class classification in machine learning. So as we have heard, in fact, in Dr. Kumar's presentation, we can use various approaches for these purposes. In fact, we have tested a number of different approaches. It turns out that for these particular purposes, decision trees are more useful for the classification, so they yield higher accuracy. For this, in particular, for this study, it turns out that XGBoost has been the most important. So for these purposes, in fact, it turns out that the bagging or bootstrap aggregation or boosting turn out to be important and helpful in improving the accuracy of the approaches. So a central challenge for understanding the results of machine learning, as also noted in Dr. Kumar's presentation, is the interpretation of the results. So interpretability, in fact, can be helped by using other approaches such as SHAP. So SHAP itself is a game theoretic approach which essentially explains the output of the machine learning model based on the idea that each feature has a marginal contribution to the results. So the SHAP approach, in fact, will turn to isolate that marginal contribution for each feature. So we're using this for such simulations for our purposes to try to understand the contribution of each of the features that we are using and its quantitative as well as qualitative contribution. So I'm just going to give a couple of examples in the interest of time. So these are highlighted, in fact, in what are called the B-swarm plots. These are very information-dense plots, in fact. So they combine the feature importance and the feature effects into one. So you may note here that, in fact, all of these points represent, in fact, the SHAP contribution at a given value. So every instance of a feature is measured and its SHAP contribution is being plotted. And then one can accumulate, in fact, all of these in a histogram for each of these plots. So then the density highlights the greater importance of that particular SHAP value. And the color code itself represents the value of the feature going between a low and a high value of the feature. So one can understand in one plot, in fact, both the contribution of each feature as well as its value. And in addition, one can understand trends between different perturbations. For example, when we remove both ligands here, so both the ATP and the substrate, one can obtain, in fact, the contribution on the positive side of the SHAP value, the important features for the structure. So in our case, in fact, we focus on all of the different secondary structural elements. So we have many such elements in one particular structure. The top 10 are listed here. So then we can glean which particular structural elements provide a stronger contribution. So as an example, we note that there is an important contribution of the secondary structural elements near pore loop 1. So these involve the helix 5 and helix 7. You might be able to see them here in this plot. And we also understand that there is an increased relative surface area and Coulomb interaction for these particular helices. So all of these, in fact, are very information rich for us. Another example is to look at the RSA and Coulomb interactions for each monomer. So if one performs an analogous type of calculation, but considering a single monomer and performing simulations, it turns out that the ATP removal has strong effects in the Sim protomers, the ones that sit close to the edge of the spiral. And then there is a destabilizing effect of the substrate removal for the non-Sim protomers. So let me summarize that in our studies, we are able to glean the complex intersubunit coupling that underlies the pore dynamics. We understand the cooperative interactions that take place in the NBD1 and probabilistic interactions in NBD2. There is a pore loop relaxation dynamics that is in close agreement with the times found in SM-FRET experiments. And then we are able to glean the differential response of pore loop dynamics as affected by BB mutations. We're also able to use machine learning to identify features that characterize the CLIP-B configurations. So all of this is made possible by the number of students who have worked in my lab and who are currently working in my lab. I want to mention in particular some of the current students who have contributed to some of these discussions, so Tarushi and Zhao Cheng and Krishan. Also, some of the former students have also contributed strongly. I'd like to acknowledge collaborators, Sue Wagner and Mike Morisi at NIH, Matt Lang at Vanderbilt, Rina Tegver at Denison, our collaborator Gilad Haran at Weizmann, and Ruxandra Dima here at UC, Christian Micheletti at CISA, and we have benefited from generous support at supercomputer centers and as well as from NSF. I'd like to especially mention a number of students from HBCUs that have joined my program over the summer, over the years, and they have made strong contributions here. So thank you so much for your attention.
Hey, thank you. I mean, this is, may I ask, this is remarkable advances on what we would call in the industry basic sciences.
Mm-hmm.
Any sense about what field of application will benefit most out of these advances? I was thinking about two things, right? Obviously the medical, but the other one was synthetic biology, where there is a lot of challenges and amazing advances on science that are necessary to be able to have fermentation, biofermentation, and synthetic biology. Do you have any sense about which field this movement will serve first?
So I think in general, one can use machine learning to try to glean specific interactions that take place at the microscopic level. So for our purposes, in fact, for protein folding itself, one can glean a set of such interactions, but one can apply the same type of approaches to surfactants, for example. So looking at self-assembly of surfactants and so on. Yeah. Mm-hmm. Yeah.
The application that can be used.
Yeah.
Next cell factory using meats, it can be for plant.
Yeah.
So just when it could be
I know that such machines are being looked at for nanopore sequences applications in particular. So in fact, because these machines have this narrow pore, they can be used in principle for sequences approaches. So that's one possibility. Yeah. Mm-hmm. Yeah. Yeah. Mm-hmm.
10, 20, 30 milliseconds. And compare it to experiments very clearly, right?
Yes. So these are in fact the extrapolated values. So our own results are on shorter timescales. So we glean them on the timescales that we have access to, but then we extrapolate using the scaling law over the long timescale. So this is extrapolated. I should make that clear. Yeah. So they would be high at this point. For us, in fact, for our simulations, they're pretty good. So we were quite encouraged by that. Yeah, yeah. So yeah, I don't have that here. So yeah, so it's shown here. So I believe that the exponent is like 0.089 or something like that. Yeah, I can give you the precise number. Yeah. Yeah, yeah.
It's hard to feel, it's difficult to access, actually.
Yeah, yeah, and with proteins, it's a particular challenge because especially at this level of description with atomistic representations, it's very hard to perform simulations over a very long time. But the important aspect of this theory is that the fluctuations that are accessible over short timescales are in fact scalable over much longer timescales. So the idea is that even as you cross barriers, in fact, the fluctuations will still remain of this type. So. Yeah, I believe that's what it is. I can look up the number. Yeah. So this is what we get in our simulations. This is this is the result that we obtain here. Yeah. One can make some arguments about compacting a polymer structure here. So I guess one can come up with some arguments, but one has to do the simulations for these purposes. Yeah.
With training your machine learning model from molecular dynamics simulations, how big of a concern is it that the individual observations that you're plugging in are correlated to one another and are not truly independent?
So that's a valid point. So we are trying to kind of do a convergence test of these results. So we do it over multiple timescales to try to glean whether the results converge. So yeah.
Okay.
Do you see like the model being expanded to